So yeah, just at the beginning. So I'm Vlada Kalinic. I'm a product specialist for SystemC in a OneSpin company. OneSpin was acquired also this year by the Mentor Siemens Group. So currently we are under the Mentor Siemens company. And the topic of this presentation will be formal verification for SystemC C++ designs. And pretty much different compared with the previous presentations because we heard many things about simulation-based verification, but currently we will talk about formal technology for SystemC. So just a few topics about formal. I guess that you are aware of the formal technology, but just to give a brief overview. So formal technology where OneSpin relies on is technology where it is helping the users to achieve the verification, I would say, faster, because the main advantage is that there is no need to write any stimulus or neither test bench, because the formal engines will drive every possible input combinations on the design side. Okay, so agenda of this presentation will be introduction and also overview of high-level synthesis usage, current challenges in our industry, and also the different type of opportunities. After that, I will talk about OneSpin, particular tool with SystemC DV inspect technology with the verify capability. And at the end, we can talk about question and answers. But also, if you have any questions in the meantime, please let me know. I will try to answer. Okay, so just a few words about OneSpin. So OneSpin has different technologies on a different area where to apply for the IC integrity. So starting from functional correctness towards with safety and also with trust and security. The main topic of today's presentation will be the functional correctness, and so I will base the story on the first part. As I said, functional correctness with OneSpin you can verify with formal with exhaustive approach the block level, but also the chip level using the formal technology with different design exploration protocol violations, integrating formal and simulation coverage, and also using the HLS SystemC verification in order to get a better quality of the code. And just to repeat that OneSpin fully relies on the formal platform. That's the OneSpin story. Okay, let's start something with the SystemC language and opportunities and also the challenges in our industry. Obviously, as OneSpin is a formal tool, the main requirements is that for the OneSpin, in order to read and to compile the SystemC code, OneSpin requires the code to be SystemC synthesizable in order to be a hardware-oriented approach. And also that's the same level and also the same requirement that other HLS tools on the market are also requiring. So using the SystemC for HLS modeling, it can create some problems, and also it can create obviously some very good opportunities. And often in the EDA industry, with various companies that are using the SystemC for the hardware development and the hardware designing, so we can face with some algorithm implementation issues, and also the SystemC language related code problems and ambiguity in the code. And obviously, as there are some types of undefined operations in the SystemC standard itself. And also one of the very hard tasks is the functional consistency between the SystemC code and also versus the generated RTL code from the HLS tool. So on the bottom of the slide, you can see the picture of the common HLS design flow. So usually the flow looks like that. Designers are starting with floating point arithmetic designs and translating in the design process from the floating to the fixed pointing. Because the floating point cannot be synthesized, and that's the reason why the fixed is used. And later in the process, going forward, the next step is to get a SystemC HLS model in order to get the all related hardware stuff in the SystemC world, like clock, reset ports, threads, input and output ports, and so on. And once that is done, that model can be synthesized in HLS tool in order to get the final synthesized RTL code. So that's the general flow in the SystemC world, hardware industry. So continuing with standard, obviously the C++ is not initially built for hardware descriptions, and that's the reason why the SystemC standard is better used for. But in the standard, there's some kind of occurrences of unspecified and also undefined, and also implementation defined, I would say, difficulties. And as these difficulties are sometimes not easily can be verified or used for the design language. So this is the reason why the verification on the SystemC level is highly welcome. Additionally, currently OneSpin supports C++ 14th version, and we are internally working on the higher, on the newer version of that to support. That's currently the status. So just a brief overview regarding with the standard and so on. And so as I said at the beginning, the current HLS flow that is used in our industry for designing is starting from algorithm model, going towards HLS coding, using the high-level synthesis tool, and producing the output of generated RTL. And it is very difficult to compare these SystemC HLS code with generated RTL, and also it is very difficult to verify the generated RTL code because it is generated by the synthesis tool, and it is very difficult to trace back if some issues are present. And that's the challenges currently in the industry. And also, if you have a code that has issues or bugs, we can say that in that case, whatever you send to the HLS tool, so as a garbage in, you will get obviously the wrong code garbage out. So this is the current some kind of challenges in the industry, and that are very extremely difficult to verify, and also very extremely difficult to debug if issues are present. Okay, by that we are suggesting, and the OneSpin has a tool to get a better quality of HLS flow with the improved HLS flow by inserting the OneSpin DB verify solution before running HLS synthesis. because the main key points is that you can start your replication much early and not wait for the HLS tool to finish with the synthesis. And also you can discover the bug detection on the original SystemC code, and also the better quality of the application, because the one-spin SystemC solution is automated, and also the push button solution, because once you load your design into the code, the tool will generate all necessary auto checks, and by that it is automated and also exhaustive, because we are using formal. And also by that you will cut your verification process. It is a much shorter way, and this is the reason why the runtime is faster and iteration loop is just shorter. And also, as I said, checking over SystemC common issues on the original SystemC code, and that's the main advantages why using the one spin pre-order HLS is very useful. Just a few more words about one spin SystemC solution. As I said, we have automatic formal analysis under the DivInspect tool, and there you can find the different categories of the checks that can point to some issues in our SystemC code, like overflow, array, out of bounds, arithmetic precision, race conditions, and so on. So I will talk about this later during my presentation. And on the top of that, also we have an additional tool, DV Verify, by which you can formally verify using your manually written SVA system value assertions your SystemC design with some specific functionality. Also, we are supporting the protocol verification IPs from the MWeb protocol, like XI4, APB, 8B, and so on. So this is just an overview of the three different technologies that one spin has for the SystemC verification. Going further, regarding the key values and also the positive things running the verification of the original SystemC code, then on the RTL verification is that you can eliminate design bugs before running HLS. You can start verification much earlier in the design process on the original on the original SystemC code, and also by that technique and methodology, you will reduce simulation effort in the SystemC and also the generated RTL. And also, as OneSpin has some advanced checks, you can help the HLS tool to get a better qualified code in order to produce a better qualified RTL. And as just to mention that also both C++ and also SystemC languages are used for HLS, and both are used also supported in the OneSpin. On the picture on the right, you can get just a feeling of the different categories that OneSpin has for the auto checks. That these are categories that are automatically generated. So just many different categories that are very useful during the verification process on the design. So I will talk about each of them later, and also I will talk each of them why these are specifically interest related with the SystemC synthesizable standard. Okay, going towards, as I said, for this tool, there is no need for test bench, neither any stimulus, because this is a formal. Any problems that are discovered in the code can be easily debugged prior to synthesis. And also that means that you can get a waveform with counterexample in order to trace back the problem on the original SystemC code. On the picture below, you can get a list of different auto checks that the tool supports in the current version. Okay, as I said, just a few words about these checks. So there are in total 20 different categories, and starting with the init checks like initialization. These are checking that all internal states and all output ports are initialized during the reset sequence. And then the next is array index. So this checks is checking that is looking for violation for the array index. The next one is division by zero, which is also one of the undefined operations in the SystemC world. And also function without return is also one of the very difficult situation to catch with the other techniques, and that's something that can produce some ambiguity in the design itself. Also, next category is shift negative, and also something with the shifting in negative direction. Also, another category, signal domain, that can check that X or Z are possible. And also very interesting, two categories that also we heard in the presentation at the beginning regarding with the process races. And so one spin has a category for write-write races and also for read-write races. So if you have two different processes, for example, SC-thread processes, and both of these processes are writing at the same time to the same signal, that's definitely a violation and can cause some very undefined behavior on your design. Pretty similar with read-write. Next to that, we have a category for overflow checking of the fixed data types like SC fixed or SCU fixed. And in the opposite category, we have integer or redundant bits. So this is very useful if you want to optimize your code regarding with the bits width of your signals. So we can point to the uppermost bits that are not used. As I said, also we have a shift category, and other two categories, process write and read without write, are developed this year per customer request. So process write is category that will generate a check and violation if you have inside one process two consecutive writes to the same signal, just as overwrite, and also if you have a reading operation without write before. So that is something that is very useful in order to discover that some undefined values in your design. Next to that, truncation or overflow checks for common SystemC types like SCUint, SCInt, int, and different data types. And also very useful dead code check or unreachable check that tool can point to the code locations that are always dead or that are always unreachable. And other two categories are stick or toggle checks. And also we have a very separate one, X checking checks that are searching for the X values in the SystemC design code itself. So if you don't have any questions, I will continue with the next slide. Just a brief overview of the tool GUI. So you can get design exploration with the instance hierarchy and also with the code of the SystemC design, and also you can get the fan-in of the signals that you would like to see. So just how the tool GUI looks like, and yeah, that's now coming the interesting part with the handling SystemC initialization. So SystemC initialization are difficult problem currently in the industry because sometimes these uninitialized registers that can have X can propagate to the logic to some intermediate registers, and also these intermediate registers that can have X can propagate on the output side with X value, which is obviously that is something that user would like to avoid. So, however, the synthesizable subset standard states that module constructor initializations are ignored. And the main reason is that receipt behavior should be under user's control. So that should be specified in the reset sequence in the thread itself or in the method itself. So these issues are very difficult to catch with other techniques, and obviously with the one spin you can get the feedback if these X values are possible to be generated on the output side. Yeah, so continuing, so with the init checks, just to get a brief overview how the tool GUI looks for. So for init category, so the tool is marking with a fail if the signals are not initialized, and with hold if signals are initialized during the reset sequence. The reason to fix this is, as written on the slide, that uninitialized values might cause X values, and to occur on the output side. Continuing the story with undefined values propagation, so about the X values in the SystemC code, we just covered the situation with the uninitialized part, but also there are other sources of X in the SystemC world, like undefined operations, like array out of bounds, all multiple drivers, like I said, for example, write traces. And what are the solutions current in the market? So we can say that SystemC emulator has no notion of undefined values or RTL semantics. And also we can tell that formal tools can exhaustively analyze all possible conditions under which an X value can propagate to the output side. Okay, and just a small hint that using the formal, you will be able to handle all sources of X, and as this is an automated app, this is also very it can be very easily used in order to get if X are possible or not on the specified design. Continuing with the undefined operations, we will talk about array out of bounds. With simulation, array addresses may be larger than number of elements, but no rate checking. Undefined behavior with also device effect, and also C++ checking tools sometimes are slow, and one of the things is that vectors, SLD vectors are not possible. And also we can mention that trivial bugs are very hard to be identified. For example, let's look at this example. So we have array with SC unit 8-bit width, and so we have a two-dimensional array, and inside the assignment we can see that on the assignment line that we are trying to write on the index location which are not possible to be fit. So these indexes are in the opposite order, and that's something that is very difficult to find and difficult to verify and to discover. Using the simulation, you will not get complaint, and your test bench will run fine. And but using the one spin, you will get violation error report. Also, pretty similar example of the array of one-dimensional array in the for loop when you are trying to initialize the same array with 10 elements, and your for loop is going from 0 towards with 10, and 10 cannot be used for the index, and also this is one of the violations that are very easily caught by the formal one-spin pool. Okay, going further, continuing with the array index violation, just a brief overview how the tool GUI looks for array index. So the tool, for example, for this example found that failure exists, so the index violation exists. And by double clicking on this fail, you can get a counterexample with the waveform and also with the active code to trace back as showed on this slide. So this is the active code with active values in the selected timestamp, and also the bottom you can find the waveform where you can drag and drop the signals in order to find the root cause of the issue. Okay, that was about array index violations, and let's continue with the races conditions. The topic that we already heard about in the previous presentations. So SystemC simulation is a sequential approach, and also the standard forces simulators to execute threads sequentially. And as the hardware is concurrent level, RTL processes work in parallel, and the synthesis result is also parallel. And this is very common used approach when you have one memory, one unique memory, for example, RAM, and you have two threads that are approaching the same memory. And in that cases, you can get the race conditions that are very difficult to be discovered. For these problems, we have two different categories: write races, as showed on the screen with the GUI represented, and as I said, if you have one signal and two different processes are writing at the same time to this signal, that's definitely the problem in your design that can cause some undefined value that can propagate through the logic. A pretty similar check we have for read-write traces. So if you have a signal that is being read from one process and also being written in from another process at the same time, this is also a problematic situation that can design be faced in. Okay, so continuing with the arithmetic precision. So regarding the fixed point numbers, like in the SystemC world, SC fixed and also SCU fixed, these so are used commonly for the designing of SystemC designs, because with fixed point numbers you can easily write or describe some mathematical complex functions, and also implementation of this fixed point also hidden from the user, and that's one thing. And also these obviously are supported, and also one spin can generate overflow checks if that is possible on these data types. Also, another problem on these fixed point is to find a proper or right bit width for the signals, because too many bits can cause the complexity, and also your design code is not highly optimized. And different opposite situation, if you have a few bits, obviously that can cause overflows and also functional errors, because you will lose the precision. These problems are very difficult to be caught by simulation, because there are too many possible combinations, and that's the reason why the formal tools are better fit in order to find and identify these issues. Continuing with fixed point precision app, as I said, you can check for overflow on different types, on signed and also on unsigned. These checks are fully automated, no need for stimulus. And also you can prove absence of overflows if everything is proven as hold. Otherwise, you can get a debug with the traces how overflow can happen in your design. Regarding with the redundant bits, the tool is checking that uppermost bits are redundant or never used. Also, this is automated app, no need for stimulus, and also fixing the proper bit widths of the signals. You can get the smaller area, and also the better optimized the code, and also you can help the HLS tool in the synthesis process, obviously. Also regarding with the redundant checks, redundant bit checks, this is the representation of the GUI, and the tool is telling that the tool found leading redundant bits. The correct number of the bits that are redundant are written in the tool shell, and that's just an example how that works. Also regarding truncation or overflow checks, the GUI representation, this is just a simple overview how that can happen. So we have an input signal that is 4-bit wide, that is multiplied with the constant 10, But on the left side, we have SC unit 5-bit signal, and obviously this multiplication of the 4-bit signal is not possible to be fit with the 5-bit signal, and that's something that can cause overflow in your design. And that's just a simple example how the tool can detect that. Also, another check is toggle or stick checks. So we can check that all bits can toggle from 1 to 0 or from 0 to 1. That something is also used for optimization, level functionality verification. And also very interesting category is dead code checks. So the tool is searching for the parts of your design code that are always dead or not reachable. Like you can see on the screen, the tool found that unreachable code is located on these 4 lines. For example, very simple code is that when you're reading the input and also with the end operation, with the negation part of the input, obviously this condition is always false. And that means that this line with temporary equals to 1 will never be reached. Okay, going further, division by 0. This is also one of the category that can cause the SystemC undefined operation, and that's something that should be avoided in any design in order to prevent the X values to be propagated to the output side. Just again, the GUI representation of the selected division by 0 check, and also for this one, the debugger is also possible with counterexample and paper. Going further, function without return. So when you have a non-void function, for example, with integer type function that can have a branch that will not cover any return. That's something that's specifically can be the real issue, and also the tool is flagging that as a separate category, no return with the failure value that function without return is possible. This is also if you want to avoid any SystemC related unknown values on your SystemC code, but also on the generated RTL code. As I said, also covering the X checks, we have a category resolution X. This is the checking that X can exist or not on the signals, but also on the outputs. Something very useful and also very easily can be executed on any design. And as I said, shift checks. So if signal can become 0 by shifting its value too many times. Okay, let's talk about other capabilities. Next to these auto checks that are automatically generated, the user can verify some specific functional behavior by using the manually written system value assertions. And you can obviously bind these system value assertions to the original SystemC code if you want to verify some specific implementation. So that's some also advanced technique if you want to check some specific situation on your design. Just a brief overview of the assertion-based verification. There are 3 types of properties, like assert or assertions, assumes like constraints, and also the cover for cover points. All these 3 types can be imported into one spin if you want to get some kind of test bench environment that can be also used at the top of the verification process with the one spin. Okay. Also, another topic is that one spin has cooperation with other HLS teams in the industry, and also we are supporting HLS libraries, coding, and that provides independent checks and also independent way of verification with using the one spin, and also the most efficient way to get the verification cleaner by using the HLS flow is that you can run the one spin of the SystemC code before running HLS2, but also you can using the one spin also on the generated RTL code in order to check for more precise verification categories. Next to the SVA assertions, also you can also insert the C asserts in your design, in your SystemC design, and also that's something that also can be easily executed. Next to that, just a use case that we got from the customers regarding with the runtimes and also with some type of checks that produce the failures or the functional issues. Just to get a brief overview of what we got for comparison with some runtimes and with issues that are discovered and that are just the comments from the public environment. So that is very easy to read and easy to debug, and faster runtime in order to reach the verification requirements. Also, just a paper and poster board that we got DVCon China as a best paper award of the used the one spin SystemC PV inspect solution on the project with SystemC language hardware process, and also at the end just a summary that by using the SystemC capability verification with formal technology on the original code, you can drive the verification much earlier in the verification process, and also you can discover the bugs much earlier, and also you can trace back much easily if you want to fix that, and also to discover what is wrong in your code. Also, this is a very automatic solution, and also that can be easily used for regression testing in the other companies. Yeah, that's pretty much everything that I wanted to share with you. So yeah, that's pretty much everything. So that's the last slide of my presentation. So I'm open for any questions.
Yes, first of all, thank you, Vlada, for this presentation. And yes, as you said, we have time for questions. Do we have anything in the chat? No. I was thinking about this, since we talk about formal, I guess we talk, if you want to compare it with some software, what software people would translate that to, that I was thinking of static analysis. So, and since it is C++, I was just curious if static analysis tools could do similar things for the analysis of this code, like like arrays and functions not returning values and stuff like that. Would that have you tried that, or have you thought of that? Like, I know at Ericsson we use this code checker tool, which we also produce, and it's very handy for software to discover errors. And I guess it's some kind of relative to formal, since it's completely static. It doesn't even run your code, it just looks at it.
Yeah, that is a very good question from you. So yes, with static analyzer tools, you can check very useful checks, and also, but not everything, obviously. And also the main difference is with comparing with the static analyzer tools with OneSpin, is that you can get the debugger, and also with the waveform, with failures if that exists, but also regarding for example with the dead code checks. This is very specific category that are very difficult to be caught by static analyzer tool.
Yes, thanks. Any other questions?
I have a question on your flow you showed in the beginning, because SystemC is step 3 in a sequence. I'm not sure if I understand that. Is that because your customers are using other tools for the first 2 steps? One further, I think next slide. No, so, a few slides back, I guess. It was yes, this one, slide 6, yes. Here, floating point, algorithmic design, fixed point implementation is in C++, and then we are going to make a SystemC high HLS model. So I do not really understand this sequence. Can you elaborate a bit more on that?
Well, usually the software designers are designing the code starting with the floating point arithmetic. And that
software, we are making, this is HLS is for hardware design, not for software. So you mean they use dedicated software tools for those 2 steps?
No, so for example, if you want to model some complex mathematical operation with using the C++ or SystemC, usually you are starting with floating point in order to get the most precise the quality of your code. But as this is not possible to be compiled in any HLS tool, because these are requiring the synthesizable standard, and definitely floating point should be translated to the fixed point implementation.
Yes, that I understand, of course. But is that not in SystemC? Why is that later? Or is that you say that it can also be SystemC from the start? Did I understand that correct? Okay. Okay. Oh, I thought that here SystemC, it somehow this is then done, and then you move it into SystemC, but it can be SystemC from the start, and that explains it.
Yeah. Okay.
Okay. Yeah. Thanks for the clarification.
I mean, just a comment, if I am an algorithm engineer, Martin, I would start perhaps with some MATLAB or some other numerical machine, some Python stuff, and just figure out what to do. And then I would be in this floating point box.
So the first one, I have no discussion. It's more probably the second box where you go for fixed point, and then you need, which is then not SystemC fixed point, but something else fixed point. And then you need to move to SystemC fixed point. So you need to go from one fixed point data type to another fixed point data type. That is not very efficient.
No, perhaps 2 and 3 can be bundled together.
Yes.
Yeah.
Yeah, that's something that is also worth it to be merged. Yeah, agree.
But question to you, Vlada, then, I mean, you said that some things are not okay, because it is C++, like initialization of values. And you said some things are not okay because it's System C. So is it your intention to try to summarize these, if you call them defects, in the System C standard and try to influence the standard so that it goes in your direction?
Well, I just wanted to present what will be the final results if you have for example, write trace on the hardware level. That's something that is I would say interesting scenario in the hardware